Hi, everyone. Thanks for coming to my talk. My name is Bobby. I'll be talking about kind of an extension of my thesis that was, at least it formed the basis of my thesis talk. And it's something we call proximal trust region methods for non-smooth, non-convex inverse problems. So I figured it'd be useful to talk about, what I did in my thesis for the CSGF meeting. So kind of a brief overview. I'll first describe the inverse problem class and why you care about inverse problems and the type of class of these that we'll be solving. And then I'll kind of go into the background of what the methods we're using, so the trust region methods and how we kind of augment that, and some of the non-smooth analysis that we'll use along the way. And then finally, we'll talk about some numerical tests that we did on a ODE inverse problem. So a key facet of scientific computing is what's called inverse problem solving, which I'm sure many of you are familiar with, but it essentially involves numerically computing parameters by minimizing some cost function, and then these parameters are used to estimate unobserved data. So just a few of these applications. It's a really broad way of scientific computing, and just a few applications that I've been involved in, whereas seismic tomography and interpolation, some seismic denoising problems, some neuron firing or biological parameter fitting issues, ODE inverse problem, sorry, and then some machine learning or neural network training is also technically a nonlinear inverse problem. So the class of problems that we'll be dealing with are, regularized cost functions, and this is essentially the sum of two functions that have exploitable characteristics. So that's in smoothness or convexity, or non-smoothness or non-convexity. And this is kind of the general problem class we'll be taking advantage of here. So in the smooth term, F contains some derivative information. Usually that's also the data misfit term, and in many nonlinear problems, it's almost always non-convex, so you're not guaranteed to reach a global optimum. And so for PDE and ODE inverse problems or machine learning, you're almost always working in the non-convex regime. But the non-smooth term, H, is usually encapsulates regularizers that promote sparsity for ill-conditioned problems. So in today's day and age, everyone has an incredibly large data set or access to a supercomputer, and the models are really, really complicated. And these large data sets encourage overfitting of your model. And often these regularizers are employed to kind of temper this model complexity. And because H is usually kind of sparsity inducing, but the very properties that make them sparsity inducing often make them lack derivatives. So it's difficult to extract gradient information and effectively optimize these algorithms, or these functions, sorry. So examples of this would be sparse regression or matrix completion or rank reduction, phase retrieval or total variation regularization. And in the literature, they're usually convex approximations of non-convex functions, which again, it's helpful, but the non-convex function is often better at regularizing than convex one. So again, why do we care about non-smoothness and non-convexity, and how can we kind of take advantage of these features of this problem? Well, they're useful, but they're difficult, right? So the problem is that, like I said, there's no global optimum, or you can't effectively take a derivative. And theory or software exists for smooth and convex counterparts. And again, nonlinear problems also have a very rich history, but they kind of require differentiability. So we kind of want to merge the nonlinear issues with these kind of non-smooth, non-convex type structured problems. So the goal of this talk would be to find an algorithm for a broad class of non-smooth, non-convex functions and regularizers, and kind of bridge the gap between classic nonlinear optimization methods and structured non-convex, non-smooth problems. Okay, yeah, so the focus is kind of give you a high-level overview of where optimizers approach these types of things. The first thing you can kind of think of optimization is roughly falling into two camps: line search methods versus trust region methods. So in a line search method, what happens is you pick a direction, and then you determine how far you walk along that direction, and how much you minimize the problem. In a trust region method, you build kind of a surrogate model, which we're going to denote M, and you kind of optimize your surrogate model over that restricted region, compare the performance of your surrogate model to your actual model. And this actually makes trust region methods pretty fast and efficient, because your surrogate model is kind of usually a cheaper version of your model. So if you have like a really expensive PDE you need to solve that takes days on the supercomputer, you kind of reduce that to a quadratic program, and then you take steps in the quadratic program until it no longer works. And kind of we'll go over how that works later. But yeah, these are often usually smooth though over smooth trust regions. And the extensions into non-smooth settings are often limited. So the contribution that we came up with is we extend these trust region methods to entire non-smooth class of problems F plus H and provide an implementation in Julia. And the tools we're going to use are what's called proximal gradient descent and trust region methods. So kind of a brief trust region introduction is that, again, they're numerically efficient approximations for usually highly nonlinear functions. And at each kth iteration, you use a surrogate quadratic model of your smooth F, and this is usually like a second order Taylor expansion of F. So you need a gradient, you need some kind of Hessian or Hessian approximation that's symmetric. And this model is valid within a region determined by quadratic model performance and accuracy. So you kind of compare how well your quadratic model does relative to your true smooth model F. And this saves numerical costs for pretty expensive forward simulations. And again, non-smooth trust region theory exists, but it's often impractical. Yeah, so in this figure, I kind of show you how a trust region method might work, where you start out with an initial trust region, initial point, and essentially you're searching for the descent step that's going to give you the minimum of your quadratic model within this trust region, right? So say if you find S naught by some method, and that method gives you to X1, and at X1, your quadratic model proves to be pretty accurate in the descent relative to your true model. So you accept that step, and then you move on to then you start at X1 with a good trust region, the same trust region because it did well, and then you kind of repeat that process, right? So from X1 you find a new step in the trust region X2. It happens to be right here. You move over there, and you're doing pretty well. So you expand the trust region. Your quadratic model is pretty accurate. So you expand the trust region, you find a new step S2 that gives you to X3, and so on and so forth. And you keep doing well, so your trust region radius is improving. So then here, say your trust region radius is actually too large because at this point, you produce a descent step where your quadratic approximation doesn't actually match your nonlinear function that well. So what happens is that you reject that step, go back to X6, which I'm going to say is X7, so these are the same point. And you reduce your trust region radius by some factor, and then you find a new descent step within that new radius, and where your quadratic model it does a little bit better relative to the true model. So from there, you move on, so on and so forth until you reach some minimum given by the star here. So in a nutshell, that's kind of how trust region methods operate. So to recap, the problem statement is that we're minimizing, some continuously differentiable f of x plus some regularization term h, and the contribution is that we created a trust region method where steps are computed by minimizing the simpler non-smooth models based on proximal gradient descent. And the results are pretty interesting because we still get global convergence. We still get worst case complexity of 1 over epsilon squared, which is equivalent to smooth cases. And we get some kind of interesting comparisons between proximal gradient and quadratic regularization as well. So kind of to dive a little bit further into the analysis, which not too much further because I don't have that much time. So the first question we want to ask is that, does the trust region theory hold? So assume we generate some step that optimizes our model via proximal gradient descent or some other non-smooth method. How do we extend the trust region theory to accommodate these kind of non-smooth, non-convex cases? And the second thing that we'll talk about is how do we actually generate this SK via proximal gradient descent? It's kind of tricky because you have an outer overall algorithm, a trust region algorithm, and an inner descent step algorithm. It's kind of a nested algorithmic problem. So the trust region theoretical results are surprisingly malleable, right? So if you adapt similar model assumptions to the non-smooth case, as you do to this, as has been done in the literature for the smooth case, you actually get similar convergence in terms of similar convergence to the smooth case trust region algorithms. So you get monotonic decrease in the objective value. You're guaranteed to produce a descent step within some trust region, i.e. you get a successful iteration at some point. And from that, you can prove that you get 1 over epsilon squared iteration complexity, and that you also eventually get first order stationary convergence. So now to answer the second part of the problem, we kind of rely on something called the proximal operator, and that's defined by these equations here, which the first one is called the Moreau envelope, and the second one is called the proximal mapping. And essentially what happens is, instead of minimizing just this h term, you're now minimizing h plus some quadratic regularization term. And the way to interpret that is now optimizing h near some x, right? And kind of, so two common proximal operators in their envelopes are kind of listed here. So this is the L1 norm. It's a typical H regularizer that you've seen in the literature a lot. And its envelope, it kind of operates as this like smoothing quadratic term at the bottom here. And for the L0 norm, which is essentially an indicator function for if it's, if x is non-zero, then it's 1. If x is 0, then it's 0. So you basically have 1 everywhere except where it's 0. And again, the envelope kind of creates this parabola around that. So it's like kind of a smoothing term, which has actually the same minimum of the h. So to determine these subproblem solutions, we need to solve this model MK, where this phi is a model of f, our smooth term, the psi is a model of our non-smooth term, and this chi is an indicator onto the truss region ball, whatever that truss region ball may be. And we're going to use something called proximal gradient updates, where for some finite psi plus chi, we generate iterates according to the proximal, up here, 2b, a solution of a gradient step in the smooth term. So essentially, how you can interpret this is saying, I want to take a gradient update in my smooth term and then minimize the non-smooth terms close to that gradient update. And this actually has some pretty interesting results. So in the literature, you're guaranteed descent for every single step, for every inner step, which means that proximal gradient will converge sublinearly to a stationary point of your model, and which is really nice because you eventually arrive at some optimality condition, i.e. a stationary point of your surrogate model. So essentially, you're guaranteed to create some descent step by non-smooth means if you use proximal gradient descent. So the recap, so for the outer truss region method, this SK created by non-smooth means still converges to a critical point of f plus h, your non-smooth cost function, and your inner PG method will eventually create this s plus k that reaches a stationary point of your model. So the next thing we're going to do is compare perform kind of model reduction on a nonlinear ODE inverse problem, and compare against two similar methods, PANOC and 0FPR. And these methods are essentially the proximal methods with, they both have quasi-Newton or Newton-like terms in them to kind of enforce speed ups and convergence. So we would like to solve this inverse problem where, so we have some data collected B and some F, where F is a solution of a system of ODEs. And we want to, again, this regularization term H of X. And this f of x is given by the Fitsu-Nagumo model for neuron activation, right? So it's a system of pretty highly nonlinear ODEs, right? You have parameters that are inversions of each other and parameters that are multiplied together. So it's definitely ill-conditioned. And what's interesting is that if you set some parameters equal to 0, it becomes the van der Pol oscillator. So that's given by this equation here. And again, so it's highly nonlinear ill-conditioned, or highly nonlinear and ill-conditioned, and we're essentially using an LBFGS for our smooth term, with H being the L0 norm and an L infinity norm truss region ball. And the goal is to exactly enforce, take data from the first problem, these 6A and 6B, and exactly enforce these parameters to be equal to 0 to kind of recapitulate the van der Pol oscillator from the data we collected, right? So this is these are kind of the results that you get from that. So if you have two neurons and they're kind of spiking, from the van der Pol oscillator, and we've collected these data, that's the points kind of around the line. The truss region method and the other method, 0FPR, do fairly well. And actually, they get they sit on top of the true line frequently, but this PANOC method actually fails pretty early on and can't converge, and that has to do with the line search stopping tolerance. So it's a line search method that can't quite compute the solution properly. Now to give you what happens in every optimization talk, where we have objective value and we see how many, how fast it can descend. So here you can see that our method descends pretty quickly, and we actually get to the true solution of x, x1, x4, and x5 equals 0, whereas 0 FPR descends in a comparable amount of time, but it can't quite hit that the 3 parameters being exactly 0. It just can't do it. Whereas again, PANOC fails quite early. It doesn't produce the right answer. So to recap, some theoretical work that we currently want to do is, can we, and something I kind of skated over here is that, we want to compute a general proximal operator computation because the size plus chi's are actually pretty hard to do. We want to extend this to penalty methods, and we also want to use different BK operators. So in the numerical examples, we use LBFGS, but we can also use LSR1, but can we extend this to nonlinear least squares or Gauss-Newton operators as well? And some practical things is that we want to finalize our Julia package so people can actually use this, and maybe extend it to C++ or add in constraints or barrier methods, and maybe try out some harder like PDE examples. So some future directions, maybe we want to look at kind of like inexact methods for PDE-constrained optimization. So currently you still have to produce this S exactly or compute a prox operator exactly. But can we get into something a little more loose and still converge? Also, something I kind of buried is that you have to produce this new k, which is based on the Lipschitz constant, which you might have to take like an eigenvalue decomposition to kind of ascertain. Yeah, and again, maybe look at some fidelity tuning for numerical simulations, or apply it to PDE-constrained inversion and CFD or Earth and climate modeling, and the huge host of stuff I'll be doing at the National Lab. Yeah, and obviously implementation into HPC like a Trillianos or role at Sandia. Yeah, thank you, and let me know if you have any questions.